Welcome to the worksheet 5 video. I'm going to go through that, give you some pointers. What must you have? What is it you must have? What must you have when adding fractions? Whenever you add fractions, you have to have a certain thing has to be true before you can combine them. What is it? You should have had that. I don't think I can bear to tell you. What is the value of an inductor if at 600 hertz the inductive reactance is 5k ohms? So now I have 5,000 ohms of inductive reactance, X sub L, and I have a frequency of 600 hertz, and I'm asking for the value of the inductance in henries. That is an equation that we've used multiple times in the class, and I'm not gonna go back over that because this is third time we've done this. So you should have that equation. You should be comfortable, and it's just an algebra one unknown problem. Number 3, what would the value of inductive reactance be at 300 hertz for an inductor that at 600 hertz the inductive reactance is 5k ohms? So basically, you've got to find out the inductive reactance with the inductance value, and then say, okay, if I go from 300 hertz where I reduce my frequency by half, what's going to happen to my inductive reactance? Now, if you look at the equation, there's a shortcut there, or you can crunch out the math, however you choose to do it. So that'll be up to you. Number 4, find the polar impedance of a series circuit, some series. So I'm adding up my resistive and my reactive. Well, the resistive part is always real. So if I come over here to my real to polar conversion, I would put my resistance in the real category, and I would put my reactance in the imaginary category in rectangular coordinate system. And so then it says find the polar impedance of a series circuit, 200 ohms resistive, 300 ohms reactive. So there's my magnitude. There's the angle. Draw the impedance triangle. So basically, here's your real side, here's your imaginary side, here's your hypotenuse side, here is one of your angles to draw the triangle for number 5. Now for number 6, if a voltage of 200, reference angle 0, was put across the series circuit containing 200 ohms, 300 ohms reactive, which we already know, what is the magnitude of the current flow? So I can take the magnitude of the voltage, 200, divide by the magnitude of the impedance, which is 360, to get the magnitude of the current flow. So basically, it's 200 divided by 300 and 60.56. That would be the magnitude. If a voltage 200, reference angle 0, was put across a series circuit containing 200 ohms, 300 ohms reactive, what is the phase relationship between the voltage and the current? So if I do the division in the last problem, I would take 200 angle 0 and divide by 360 angle 56. And so when I divide polar complex numbers, I would subtract angles, 0 and so it'd be 0 minus 56.31, and that angle would be the phase relationship between the voltage and the current. And that would be the answer for number 7. What is the VA of a system with 200 volts applied across a series circuit containing 200 ohms and 200 ohms resistive and 300 ohms reactive? So now we're heading into the power triangle. So we know the voltage and you know the current because we have the angle. So my voltage is 200 and my angle is 0. My current is 200 divided by 356, which go ahead and make it an equation. 360, sorry. 360.56. And my angle will be 0 minus 5631, which is just minus 56.31. Just like we did the impedance triangle up here, we can now do a power triangle using these values. I have voltage, and I have current, and I have the impedance. So I have the impedance, or the Z here. Now, what's the VA? So VA is volts times amps. So 200 times 0.554629. So I'm going to multiply my volts times my amps in complex. So my VA, which is number 8, is equal to 200. And when you get good at this, you'll just reference the cell. As a matter of fact, I'm going to do that. The number here in E4, I don't feel like typing out, so I'm just going to say times E4. It'll reference the cell 2 above it. So my VA is 110. Now when I multiply angles in polar complex numbers, I just add them. So my angle will still be the negative 56. 0 plus a negative 56.31 is just equal to, I guess that's F4. So this is my VA. And how much power is dissipated by a system with 200 volts applied across a series circuit containing 200 ohms? Now VA is not power. This is the hypotenuse of my power triangle. This is the angle of my power triangle. What I need to know is my VARs and my power. So to find my VARs and power, I just got to find the real components of this. And so I come down here to my handy dandy converter and I say E6 equals E6, enter, and my angle would be F6 equals F6, enter. And what you see here is I have a triangle. This would be my real component. This would be my imaginary component. This would be my hypotenuse. And this would be one of the two angles that are not 90. And it's a right triangle. So here's my VA value. And what I ask for is how much power is dissipated by a system. Nothing's changing in the problem. I'm just asking for the system. Power. So the power then becomes my real component. So that circuit would dissipate 61.54 watts. How many VARs are there in a system with 200 volts applied, 200 ohms? And my VARs are actually 92.31. The fact that there's a negative, inductors will wind up with negative VARs, capacitors with positive. And what we will see eventually is they will tend to cancel each other out. That's a later worksheet, but it's soon coming up. So my VARs is 92. The fact that I've got the minus, that just gives me the phase angle if you will. So that's the VARs. The power factor of a system, same system, I'm not changing anything, is the ratio of the power, which is the real component, to the VA component. And it also happens to be the cosine of the angle. So if I take the cosine of this angle, I'll get a ratio. And that ratio should be the same ratio as my real to my VA. So my power factor is A13 divided by E6. Whoops. Got to start with the equal sign. E6. That's my power factor. Notice it's the cosine of the angle of my impedance triangle too, right? No. That's my power factor ratio. Did I do that right? I think I did. A13. Thought about E6, yep. So that's my power factor. I've got a 0.55 power factor for that particular circuit. Draw the power triangle. So again, here's my real, here's my x-axis, my imaginary axis, my VA, and one of my angles. So that would be my power triangle. How does the power triangle compare to the impedance triangle for the same circuit? And what you'll see is that my impedance triangle, which was made up of this line, compares very nicely. Matter of fact, they're actually called similar to the power triangle. Okay, that's going to pretty much finish that circuit. 14, we're going to start into capacitance. Measure the resistance of a capacitor given to you by your instructor. What you should see typically is capacitors don't have a resistive value, but they seem to charge. So you might see a resistance value that changes, but you're not going to be able to come up with a specific value like we did on the inductor. And then check the value of capacitance using a capacitance meter. Some of our bench meters have it, some don't. There are capacitance meters in the back of the classroom. And then how does it compare with the printed value? For number 16, we're going into capacitive reactance. It's a formula I introduced in DC last semester. It's capacitive reactance, X sub L, is 1 divided by 2 pi times frequency times the value of the capacitor. So it's just an equation. It's similar to the inductive reactance equation we started to up on top, but it's got a reciprocal part, and I'm asking you to do it at 3 different frequencies. What frequency would the capacitive reactance equal 0? If you look at the formula, when would it equal 0? What frequency would the capacitive reactance be infinitely large? Same questions I asked on the inductor, but you will see that it's opposite the inductor. And at what frequency would the capacitive reactance of a 37 microfarad capacitor and the inductive reactance of an 800 millihenry inductor be the same? Now I'm comparing the inductive reactance equation to the capacitive reactance equation. And basically I'm setting them equal, and I'm solving for the frequency. And that's going to be a special frequency that we'll get into a little while later. And then given a circuit with 56 microfarad capacitor, a 3K resistor, what frequency will they be the same? So now I'm taking the capacitive reactance formula and I'm setting it equal to 3000 and calculating the frequency. And that's going to be my special frequency like we did last time, and it'll be a corner frequency. And that's that basically gets us going and gets this worksheet done. It's not too bad. Nothing to build this time. Just a lot of stuff to calculate and figure out. Anyway, thank you for watching.